Well, that was pretty dumb. uh, believe it or not, the idea to do that little thing with the terminal was proposed 19 minutes ago. So, in case you were wondering about the quality of my typing or anything like that. Now, it is such an honor to have you all here today. My name is Colin McDonald. I am the head of developer relations at EdgeDB. This has been a long time coming. EdgeDB has been under active development for 4 years. We've had 7 alpha versions, 3 betas, and 5 release candidates. And yeah, any scenario where there's been 5 release candidates of a piece of software, there's a story there filled with blood, sweat, and tears. I say all this to say that we take the task in front of us very, very seriously. We know that choosing a database for your application is maybe the single most important decision that you make over the course of building a product or a side project, or really whatever you need a database for. And we understand the burden of that. And when we say that EdgeDB 1.0 is finally here and it's ready for prime time, that we really mean it. Now, it's been a tremendous honor to have any part in EdgeDB's history here, especially to be with EdgeDB at this epic moment in time. I am beyond excited to see what happens now that EdgeDB is out there in the world, that 1.0 is here, and people can start using this new database abstraction for the first time. I'm going to cut myself off there because I'm just the MC, and this is not the keynote. I just have a lot of feelings, I guess. So before I get myself in trouble, I'm going to hand it off to co-founder of EdgeDB and our CEO, Yury Sullivan.
Thank you, Colin. Hi there. So excited about this. Today is a big day for us. And I believe that's true not just for EdgeDB, the company, but for the entire database community. New database products don't launch often, but new categories of databases basically launch hardly ever. For example, relational databases were introduced in the 70s and were revolutionary. But the next big shakeup of the industry didn't happen until around 2010, when NoSQL movement was started. We believe that EdgeDB defines a new category of databases, something that has an opportunity to forever change the way we think about data and how we work with data. So buckle up and prepare to spend some time with us today to be the first to witness the dawn of post-SQL era. Although, before we begin, I would like to thank you all for joining us here today. Some of you must be new to EdgeDB, and I hope you'll love what we're about to show you. Special thanks go to those who have been following us for a long time, submitting GitHub issues, pull requests, proposing new features, beta testing pre-releases, and most importantly, encouraging us to continue pushing forward. We really want EdgeDB to be community-driven. Together, we can finally make a developer-first database a reality. But before we start talking specifically about EdgeDB and why it is so special, let's reflect on the history of relational databases a little bit. Picture programming in the 70s. Okay, it's not so easy to do so actually, right? Not all of us were living, let alone programming those days. Spending some time on Wikipedia helps to imagine what it was like. Computers were basically things of science fiction. It was a few years before the advent of personal computers. Big businesses needed mainframes, which were essentially room-sized cabinets and required certified operators to help them to keep them running. Punch cards were very much a thing. It was about this time when relational databases and SQL were invented. And to be clear, the severe limitations of compute and storage actually had a positive impact on the relational databases design in general. The relational model avoids data duplication. It's flexible enough to represent almost anything. Most importantly, the model doesn't have any requirements around how data should be stored at the physical level, which, for example, open doors to the modern columnar databases and many other things. By all means, relational databases were extremely cleverly designed for the time, and this is the reason why they dominate the database market today. What database designers truly didn't have access to 50 years ago are modern programming languages and software architectures. Relational databases require us to think in tables, but that's just not how we think when we are writing JavaScript or Python code. SQL was designed to essentially allow businessmen implement reports in an English-like language. There was simply no requirement to make SQL composable or to make it play well with any programming languages. The solution to the I don't like tables problem is using an object relational mapper library, ORM for short. Invented roughly 30 years ago, these days using an ORM is almost mandatory. Many use existing libraries, few can afford to build custom data layers, but the fact is that most don't want to interact with relational databases directly at all. They're always enveloped with layers upon layers of abstraction and various services. This would all be okay if only ORMs were great. Unfortunately, they're not. Because ORMs typically support different databases, they sacrifice performance for compatibility. Their APIs are usually non-composable and very complex. They require you to essentially write SQL by hand even in slightly non-trivial cases. Most of the amazing engineering that goes into relational databases is not accessible with ORMs. If you use one, you likely use 10% of what your database is truly capable of. And this is where we finally want to say enough is enough and introduce you to EdgeDB. Our goal with EdgeDB is to eliminate all extra layers of abstraction. The database must feel like an integral part of your stack. You should have zero mental overhead when you work with your schema, when you're writing queries or do database maintenance. No ORMs are necessary. We just want to forget about their existence. This is a classic example of easier said than done though. In order for us to do this, we had to rethink basically the entire database stack from top to bottom. So we started with the most fundamental layer naturally, the relational model itself. We enhanced it to basically turn your data into a graph while retaining most of the relational fundamentals. We call this new relational model extension a graph-relational model. And naturally, EdgeDB is the first graph-relational database. While working on this new model, we are also designing a new query language. We call it EdgeQL. And EdgeQL looks like a child of SQL and GraphQL, and that's sort of intentional. Like with GraphQL, you can select nested data, access your graph. Like with SQL, you can perform computation. EdgeQL has functional roots, so it's extremely composable. Working with it feels like writing code with a high-level programming language. It's a perfect target to build data APIs with. We spent years designing EdgeQL, and the end result is a powerful, easy to learn, and just a beautiful language to use. So far, so good, you might say. What else? To which we can answer, hey, this is just a tip of the iceberg. First, it's an open secret in the industry that relational databases are just not ready for cloud or serverless. This is a big topic that deserves a proper talk or blog post on its own, but let me just say how we made sure that EdgeDB will be ready for serverless. EdgeDB can handle several orders of magnitude more concurrent connections than your typical SQL database. Our client libraries can automatically recover from network errors and replay failed transactions for you. We engineered our communication layer to minimize the number of round trips between the database and the client. Often you just need one network packet to send a complex data operation and just one to receive the result. Second, with EdgeDB, we are not just building a new database for you. We are essentially redesigning from scratch the entire front end of the database. Just let me cherry pick a few cool things. For example, we spend a great deal of time making sure that our client APIs are simple, idiomatic, and fast for all languages that we support. That's currently Python, TypeScript, Go, Dino, and soon Rust. Our command line tools and the interactive shell are just best in class. You have to experience them to see for yourself, but trust me, we are obsessed with making them feel amazing. And while EdgeQL is a much more powerful and expressive language than GraphQL, by now you probably get the theme, and you know that we are not fans of hiding the database behind layers and layers of extra services, so EdgeDB supports GraphQL simply out of the box. And when it comes to evolving your schema, changing it, we have you covered with first-class migrations. This is perhaps one of the biggest pain points with relational databases that EdgeDB makes a thing of the past. So there we have it. EdgeDB 1.0 is here. It is fully open source. It's ready for you. But we don't want to stop at making it open source. We want to make our new graph-relational model and our query language EdgeQL an open standard. Our journey is no longer about just building a new database. We want to start a movement. We want to finally change the status quo. We want to finally have a database that we, software engineers, truly deserve. We have a great lineup of talks for you today. My co-founder Elvis is about to tell you more about the graph-relational model and demonstrate what it can do for us. We'll have live demos, talks that give an overview of our schema, compilers, and the server architecture. Stick to the end to hear me once again talking about the short and long-term future of EdgeDB. Thank you so much. Back to you, Colin.
Awesome. Thank you, Yury. We've got a great show for you tonight. Like Yury alluded to, we're going to be doing a series of lightning talks for the next hour and a half or so, hopefully get you out of here within that 2-hour limit. Before we jump in, a few quick programming notes. Each talk is going to be roughly 15 minutes. We've disabled comments on the YouTube live stream. That's intentional because YouTube comments are notoriously terrible. Instead, we're actually using our Discord. So if you check in the link, the description rather, of the stream, you'll be able to join our Discord. The launch channel is going to be sort of the comments section for this entire event here. So feel free to discuss anything related to the events or the speakers in that channel. And if you have any questions, put those there too. We're going to be keeping an eye on that. And at the end of each lightning talk, we're going to be doing 1 or 2 questions from the Discord. So let's just jump right into it. We're going to be doing a couple talks here back to back about the lifeblood of EdgeDB, which is its query language, EdgeQL. So without further ado, I present to you co-founder of EdgeDB and CTO, Elvis Pranskevichus.
Hello, everybody. Thank you for joining us. I'm Elvis, co-founder and CTO of EdgeDB, and today I'd like to talk about EdgeQL, which is, of course, the query language of EdgeDB. I'll try to explain why EdgeQL is necessary and why it's a better query language for the future. Of course, this is a lightning talk, so I'm mostly going to be showing things. But before we begin, let's talk a little bit about the current state of things. So about 30 years ago, the world has decided that the majority of programs would be modeled and written some object-oriented programming language. But also that those same programs would store most of their state in some SQL database. Unfortunately, we immediately realized that this is far from ideal and problematic enough that we came up with a name for the issue, object-relational impedance mismatch. And of course, impedance comes from the electrical engineering field, where mismatching impedances cause an electrical circuit to be a lot less efficient. So this is the same for software systems. Coupling relational databases and object-oriented programs is not efficient. And a lot has been written about this, a lot of solutions proposed, but unfortunately, it seems like our database tools, or at least our database APIs and frontends, are barely more expressive or efficient than they've been in 2005. So it almost seems like object relational mismatch is an inevitable fact of life, and we should just accept it. Except, of course, it isn't, and we shouldn't. Object relational mismatch isn't some law of nature. It exists primarily because we let it. And of course, the reason is that the SQL database world is fairly slow and is either unable or unwilling to fundamentally improve things. On the other side, the application development world has been stuck in the losing war of perpetually writing and rewriting countless object relational mappers or ORMs. And there are really dozens of public ORM libraries for every programming language and likely thousands of in-house ones. I know this because during the course of my career, I wrote 4 production ORMs. So imagine the collective level of effort expended to write and maintain those ORMs and then inevitably fight them because sooner or later the facade of abstraction just falls apart due to how shaky and inconvenient the SQL foundation is. And of course, I also have to mention NoSQL, which is an attempt to deal with the whole problem by removing the relational part altogether. But the reality is that the relational model, the strict schema, and high-level abstract query language are actually very, very useful. And so NoSQL will likely always remain to be no more than a niche. So what do we do? Of course, the answer is simple. We kill the table. Basically, what that means that we need to adjust the database model and replace SQL with something better. And before we discuss how, let me show you a simple example. So as you might have noticed, we're quite fond of movies at EdgeDB. Lots of our examples are based around some movie-themed schema. Let's continue this tradition and perform a simple task. Select the titles of all movies in our database. So EdgeQL is on the left and the equivalent SQL is on the right. So far, so good. The results are quite similar, short and sweet. Now let's expand things a little bit. Fetch a list of actors for every movie. It's pretty easy to do in EdgeQL. We simply add another entry to our output shape, which is quite self-explanatory and looks a lot like GraphQL. SQL, on the other hand, is suddenly a lot more verbose because we now have to tediously specify the relationship joins and we had to type a lot more. But the worst part is that our solution is only approximate because SQL returns a flat list of tuples instead of a nested structure, but EdgeQL does give you actual grouped result. And we'll talk about this later. Let's move on. Simply selecting existing data, of course, is boring. So let's compute something. In this case, an average review score for every movie we selected. In EdgeQL, we simply call the mean function on the set of all associated review scores, like so. And SQL doesn't do too bad either. It's more verbose. It needs an explicit subquery for aggregation, but it's okay. Now, we rarely need to select everything, so let's add an interesting filter condition. Let's say get all movies where Zendaya played a role. In EdgeQL, it's again a simple operation on an associated set. And in SQL, we've got a similar construct, except again, we need a subquery, we need the verbose joins. And by this point, you see a clear pattern that you have to repeat the joins over primary keys over and over again, making everything unnecessarily verbose and hard to read, even for simple cases. Well, let's add a final touch. Movie casts are long, so let's say we only want to fetch the first top 5 actors in the first 5 actors in the credits order, because we don't want all the extras and whatnot. So in EdgeQL, it's very easy. Again, we added an order by operator and a limit. And in SQL, unfortunately, we had to rethink the whole query. We cannot just slap a filter and a limit on the entire query, because we want to slice the associated actor set for every movie. So we had to resort to adding a lateral join. And lateral joins actually is something that is fairly new to SQL databases. They didn't exist around about 2015. And some popular databases like MariaDB still don't support them. And the public is generally not very aware of their existence. And it's fairly advanced stuff. So anyway, here's the finished query. EdgeQL, as you can see, can still fit in a single tweet, but you'll need a medium post for the SQL query by this point. And seriously, this shows how quickly SQL becomes a very unwieldy and unergonomic mess. And this matters very much, of course, because your ability to quickly and effectively express things is the cornerstone of your productivity as a developer. So now let's take a quick step back and take a look at ORMs to compare, because theoretically, ORMs should solve some of those problems of SQL and improve the expressiveness and let us do more things with less. So this is our query implemented with Prisma, which is the current state of the art of ORMs, at least within the JavaScript community. And at a glance, this query looks all right. The nested structures of related data is expressed nicely. The filters are there. However, unfortunately, we see that an important bit is missing, and it's the average review score. And this is because Prisma, like most ORMs, lacks a way to actually compute arbitrary expressions in your queries. And so in this case, we have to perform a separate query and then manually join the results, which almost doubles the amount of code. Not only that, under the hood, Prisma actually does 3 queries to fetch the list of movies and hides it from you. And that's because it simply cannot get away from that inability to express nested sets in SQL generally and efficiently. And remember, this is pretty much the state of the art as far as ORMs go. And if you try any other ORM, the results would be fairly similar or worse. And the bottom line is that it's really hard, almost impossible, to build an efficient object abstraction over generic SQL that supports multiple database implementations of multiple versions. So let's see what would happen if a similar native query language builder targeted EdgeQL instead. So this is our familiar movie fetching query on the left again, and here it is on the right, expressed using our JavaScript query builder library. Remarkably, the JavaScript formulation not only follows the EdgeQL query structure line by line, it's also not much longer. And the best part of it is that this is still a single query, guaranteed. This is a single round trip to the server. And again, let's look at it side by side with an earlier Prisma example. So you can see, how big the difference is. And this is simply because the query builder in TypeScript targets EdgeQL and not SQL. So now that you've seen it in action, let's talk about what makes EdgeQL so unreasonably effective. And the answer to that is we took the classic relational model and extended it just enough to realize these 3 core concepts. Object identity, and it's the requirement that every piece of data must have a unique immutable key that is independent from the data itself. So it's things like auto-increment ID fields that you have to specify everywhere explicitly in the relational model. You don't need to do that anymore. That's just there. It's an inherent property. Second, links, which builds upon object identity, but it's a formal acknowledgement that data is referencing each other in your model. So you don't have to do foreign keys. You don't have to do explicit joins over primary keys verbosely like you do everywhere else. And last but not least, we made it so that everything can be a set. And this is really important. Object properties, query results, and those sets can nest, so you have nested collections of data. And like a previous example has shown, the associated movie actor list is not, it's really trivial and easy thing to do, and unlike SQL. All right, so let's quickly take a look at another example. In EdgeQL, everything is an expression and everything is a set. So this means that you can replace any value with an equivalent expression and vice versa, which means that you can write queries like you write code progressively. So let's take a look. We have a new variable movie title, assign it to Avengers. Now we have another variable actor names, which is a set of names. And now we have a set of actors, which are actual objects that we select from the database using the set of movie actor names. And finally, we insert a new movie object using the variables we computed before. Of course, this is a fairly trivial example. Let's look at another one. Again, we have a set of movie actor names. We select those actors, and now we insert the movie. But note that insert statement itself is also an expression, so you can just write it and assign it to another variable. Let's insert another movie. So now we've done two insert statements within a single query. Now let's say we wanted to update our watch list on some Netflix kind of application. So we select the user account using their login query argument, and then we update that account by adding the newly inserted movies into the watch list of that account. So, and this shows how EdgeQL is actually really, really close to a normal, straightforward programming language. So you don't need to think, oh, what's the declarative syntax for this very simple operation? It just flows normally, like you expect it to. All right, so let's recap. Big ideas of EdgeQL. Graph-relational data model, which solves practically every issue in the object-relational mismatch, right? It lets you traverse, mutate, extract arbitrary graphs of data, semantic graphs of data. Fully defined modern type system. And what this means is that unlike SQL, that the SQL standard actually amazingly doesn't include a type system definition. It's not defined, it's implementation specific, which is why every SQL database has its own set of data types and behaviors. In EdgeDB, we actually have specified that data model, and there is a rich library of standard data types, including things like arrays, tuples, collections, all types that you expect to be there in a modern query language, in a modern programming language. EdgeQL is a straightforward compilation target for language bindings. Like I've shown you before a sneak peek of the JavaScript query builder, and you'll see a lot of it in subsequent talks. Really exciting. It simply because it's so composable, and the organization of EdgeQL lets you use it as a compilation target really easily, unlike SQL again. SQL is really, really hard to compile to. And EdgeQL, and this is very important, it's intended to be a complete SQL replacement. And what it means is that whatever you can do with SQL, you should be able to do with EdgeQL, only in a shorter form. And if you can't do something with EdgeQL that you can with SQL, it's a bug. Go and pester us on GitHub, and we'll fix it. And lastly, what all of this means is that object relational mismatch is essentially gone, right? We tweaked the model from the bottom. We're not trying to solve it from the top like all the other solutions are trying to do and have been trying to do for decades. And this essentially removes the entire need to write complicated client-side libraries altogether. And so the biggest takeaway here is that we can and should do better than SQL. And EdgeDB is here, EdgeQL is here, and that time is now. Thank you very much.
Awesome. Thank you, Elvis. That was phenomenal. We've got a question coming in from the Discord. I'll paraphrase here. EdgeQL looks very neat. Is it based on any sort of has any sort of theoretic basis, and what is the relationship to relational algebra, if there is one?
Right. So, like I said before, it's based on an extension of relational algebra. It's still fundamentally underneath a relational language. What we've done, we've extended the relational data model to add a concept of a reference type, which, but in the relational model, it's not defined explicitly, right? So you're supposed to be doing joins over candidate keys. So what we've done, we've added those keys and the concept of relations directly into the model. But everything else is essentially builds upon that. And the set valued attributes that everything is a set. So basically, given those two additions to the relational data model and turning everything into a set, and then just simply using set theoretic operators on those sets consistently, and that you get EdgeQL.
Fantastic. Thank you again, Elvis. Let's jump into the part 2 of the EdgeQL series here, which is going from the big ideas to some of the nitty-gritty of how to actually use it. So I introduced to you senior software engineer and guy without which EdgeDB would fall apart immediately, Victor Petrovic. Take it away, Victor.
All right. Hello, and welcome to this EdgeQL primer. My name is Victor Petrovic, and I am a senior software engineer at EdgeDB. So we'll pick up kind of where Elvis has left off, but we'll dive into more details about EdgeQL. And the best way to do it is by trying out to build something with it. So we'll go and try to model something familiar, like the Netflix clone we already used in a previous example. And to keep things simple, we'll ignore all the complexities that come with setting up user accounts and profiles and such, and we'll concentrate instead on the movie library aspect of our Netflix clone. So, where do we start? Well, we're gonna need some movies with titles and maybe release year. And here's a type movie. It has a required title property and an optional release year property. So far, so good. But we're gonna need more. And movies have directors. So we'll represent that with a new type and define a relationship like so. There's a new type person now, and there is a link director from the movie to the person. It's a single link, so there can only be one director per movie. But movies also have actors, so we also add a multi-link actors to the same type person, representing the fact that every movie can actually have multiple actors associated with it. Well, there is some other information that could be useful. Actors play characters, and it would be really neat if we could store the character names somewhere. And there is a way to do so. We can enrich the actor relationship by adding a link property to it. And this is basically a property that's directly on the link, and we'll call it character name. And this will encapsulate the information of basically the triplet of who played in which movie what character. Now, this is going to be a big Netflix clone with a big library of stuff to see, and there's going to be more than just movies. There's going to be shows with episodes and such. So to represent these shows, we're going to need another type similar to a movie with a lot of the same things like title and actors, but maybe we don't have a release year because it's not quite as clearly defined for a show, and director is also not as clearly defined. On the other hand, we will have a number of episodes specified. So the show will look something like this. Well, that looks like a lot of copy pasting, and that's not exactly ideal in most programming settings. We want to avoid copy pasting as much as possible usually, and we can do so in EdgeDB by using a mixin type. And we factor out all the common links and properties into this mixin abstract type content. We make our movie and show extend content. And now movie and show only need to contain the links and properties that are specifically unique to them and without any duplication. So what else? We have this release year number of episodes, and we just selected int32 to represent them, which it's okay, but it has negative values, which is not ideal for our case, and maybe we would like to restrict that. We can add constraints to our schema to make sure that completely unreasonable values don't get entered into our database for release year and number of episodes. And we have a built-in, we have a number of built-in constraints. We're going to use the min value constraint specifically here to generously give the minimum value of 1900 for the release year. We're pretty sure nothing earlier than that, and even that is very generous, will appear in our movie library. And for the shows, the number of episodes will be kept at 2. Well, now that we've set up the schema, we can actually get to querying. What should we start with? We have a Netflix clone, so we're going to have some kind of a movie page with all the information about the movie. So let's build up that query. Well, if we just select a movie, we get a bunch of objects with just IDs in them. And if you remember, actually, this is a good time to mention that we didn't have to specify the fact that the objects have ID property. That gets included by default into every object. They will all have unique IDs for us to use. Well, that's all nice, but we actually need a lot more data to make it usable. So we add what we call a shape. Inside these curly braces, we write the fields that we want to fetch. And this may look actually similar to GraphQL, and it works in a very similar way. So here we added some properties that we're now fetching. Going forward, we can actually nest these shapes inside each other. So in addition to the movie shape, inside of it, we can add the director link and add the name to its shape, and actors, and add their names too. But there was something else we actually had. We had the character names for the actors, and that would be also nice bit of information to include in this query. But the character names were not a property of the actors themselves. They were the property of the link. So there is special syntax for that. We use the @ symbol to indicate to EdgeDB that this property is actually a link property rather than a property of the object. Now, finally, we added a filter, because this is going to be a page for a specific movie. And so we just select filter movie by title here. Notice that filter is using movie.title, and we call that expression a path. Basically, any dot-separated expression is a path. It starts with some object, it follows a bunch of links and properties to get to the final set of values that it needs to consider. And the thing about the path is that this movie here is actually referring to the movie we're selecting. So we're saying select a movie with a whole bunch of stuff in it, and use the movie title in the filter. Now, there is a shorthand for this because quite often we end up referring to the thing we're selecting. And the shorthand is just start a path with a dot. What that means is that the path starts wherever the scope of this expression is. So this expression appears in the scope of selecting a movie. So movie is the scope, and dot title becomes movie.title internally. Well, now that we have a nice query for our movie page, we can tweak it to provide a different kind of query to maybe use in suggestions. So it looks pretty similar. There is our title release here in director. We drop the actors subshape here. And the filter is different now because instead of selecting a specific single movie, we are instead getting suggestions based on the actor who played in the movie. So you can also see that we're using the abbreviated path here as well. So this .actors.name refers still to the movie.actors.name. Now, of course, since this is going to be used in our suggestion widget, we don't want to overwhelm it by giving all possible results. Instead, we're going to order them by release here to keep the most recent ones on top and just select the top 5 using the order by and limit clauses. However, there was another thing that query didn't do. It was only selecting movies, but we actually have movies and shows in our database. So instead, we're going to use this polymorphic query, selecting content, which is the abstract base type, both movies and shows extend. And inside of it, we will specify different properties and links that it should include depending on whether this content is a show, and then it should include number of episodes, or is a movie, and then should include the release year and the director. So the query stays largely the same, but now this polymorphic query can extract uniformly all this information regarding shows and movies based on an actor that start there. Well, we probably want an actor page as well, or at least some kind of way of displaying some actor information, but the actors only have one property in our schema. So wouldn't that be a bit of a problem? Well, we can include any arbitrary computed information in our return shape. And to do so, we use this defined as symbol, also known as the walrus operator. It's a colon with an equals. And for our example here, we just use a built-in function to split the actor's name into the individual components as just a showcase of how to use these arbitrary computed expressions. However, these expressions are in fact arbitrary, so let's compute something else that's maybe a bit more useful, like the number of movies that this particular actor has starred in our library. So we do a movies count, and we again use a built-in count function and a subquery. This is fairly simple and reasonably intuitive subquery, although it's worth mentioning that we're selecting movies where the actors, where there is this person that we're selecting among the actors. So the person in the subquery is actually the same person object as we're selecting. And this is all fine, it works, but this is a bit bulky. there's actually a better way of doing this. Anytime that what we seem to want to do here is we seem to want to use the actors relationship, and instead of going in the usual direction from movie to a person, we want to trace it backwards. And to do that, we have backlinks. So we use the special symbol for the backlink. It's instead of a dot, it's a dot with a back arrow, which says follow the actors link backwards. And then we also add this is movie construct there, and we're already familiar with it from our polymorphic queries. And overall, this will get us from the person we're starting at, following the actors link back to the movies that refer to them, and get us all those movies, which we can now count. Well, that backlink stuff is actually quite useful, and wouldn't it be nice to add it to a schema? Well, we actually can. We can define this computed link in movies directly in the schema, so that we don't have to retype the backlink syntax all over again. Let's add 3 of the most recent movies that the actor appeared in our data, because just saying how many is probably less interesting than showing the recent features. So again, we start with a query that should be familiar. We're fetching the person's name and movie count, and in the count now we're just using the computed link we defined in schema instead of the backlink explicitly. And to add the 3 recent movies, we follow this computed link in movies. We fetch their title and release year, and then after this shape, we order this entire thing. We order it by release year in descending order and select the top 3 again. This gets us our actor information, including the number of movies they starred in, as well as the latest 3 features. Of course, EdgeQL is not limited to selecting data. We can also insert, update, and delete stuff. And here's a little teaser for a nested insert. It uses the defined as, or the walrus operator, to insert the data, except that unlike in the selection queries, of course, all the links and properties mentioned here must actually exist on the object into which they're being inserted. The fact that it uses the same expression as the computed expressions suggests that actually any valid EdgeQL expression can appear on the other side of this operator. And indeed, for director here, we include a subquery that inserts a new person record. We could have instead used the subqueries that selects an existing record or anything else, as long as it produces a person at the end that we can assign as a director. So like this, we have a nested insert which creates 2 objects and links them together. Well, this concludes the primer, and really, there is so much more to EdgeQL than that has been presented here, and I hope this has piqued your interest enough for you to actually go and try us out, read the docs, and discover all the power of EdgeQL that is available. Thank you.
Awesome. Thanks, Victor. We got a question here about the actual data modeling surrounding links. Specifically, the sample schema didn't contain any one-to-one links. You want to talk briefly about how to model this?
Sure. So one-to-one links are kind of interesting. They usually arise whenever you want to basically split a big object into smaller components as a form of type composition. The one-to-one links would, in fact, look very similar to a regular link, except they would need. So the link director is a many-to-one link. It has a single target.
You'll have to share your screen again if you're on slides.
Let me share the screen again.
Perfect.
Okay, so I have the slide here. So the link director is a many-to-one link, and it has a single target, but it has no restriction on how many movies can reference it. So in order to restrict it and transform it into one-to-one, we need to add a constraint to it, and it's called an exclusive constraint. Basically, similar to how we added the min value constraints to our properties, you can add an exclusive constraint to a link or to a property. And that way, you could turn a many-to-one link into a one-to-one link.
Okay. Thank you, Victor. Fantastic talk. And it leads perfectly into this next one, where we're going to take some of that stuff we just learned about EdgeQL querying and actually do a live demo of a simple application. So we'll see how this goes down. I'll be the one giving this demo. So let me quickly share my screen here. Drag some windows around. Nice big terminal. I'm going to be actually following, I'm going to be building off of a repo that's actually public here. So I will share a link to this in the Discord quickly. So if you want to follow along, there's the chat. There's the link to the repo. So it's going to be building basically the world's simplest to-do app is the idea. So we're going to get started from scratch here by cloning this repo, going into that directory, and then installing some dependencies with Yarn. This is all going to be JavaScript based. This is an application that is built with Next.js and TypeScript. So just so you can kind of see what this looks like, let's run this application and see what we have initially. There we go. Cool. So this is what we have at the outset. It's a simple app that I've implemented, but it's totally backendless. There is no actual data persistence here happening at all. You can, in fact, you'll see in a second that these to-dos here are just statically hard-coded into my backend. There's a couple mutations that we have available, so you can add to-dos, which doesn't work because I haven't implemented it yet. And you can toggle them, of course, which also does not work yet. So the first step in building any kind of application with EdgeDB is, of course, to install the CLI. If you go to the install page on the website, you can grab the command for your operating system. I already have this, so I'm not going to do that again. Let me quickly open a second window here. Okay. So as you can see, I've got the EdgeDB CLI already installed. EdgeDB version is CLI 1.0. I cannot tell you how exciting it is to see that 1.0 there. That is fantastic stuff. So now that you have the CLI installed, there's really one maximally simple way to get started building any sort of application with EdgeDB, and that is EdgeDB projects, which is a CLI concept. So the way that you get started with that is go into your product directory and run EdgeDB project init. This is a kind of interactive way to set up a database for a given project. This is primarily a development tool. So what it does is when you run this command, it prompts you to initialize a new project. prompts you to specify the name for that instance and which version you want to use. What's happening here under the hood is that it's spinning up an EdgeDB instance for us. If you only have the CLI installed, but you haven't installed any actual versions of EdgeDB itself, it automatically installs those versions for you and detects your operating system. Another thing worth noting here is that it spun up that instance, and it linked it. We say it linked it to this particular project directory. In practice, what that means is all the instances that you create with the CLI, it basically keeps track of all the running instances, as you'd expect, including the credentials for those things. So, the name of the instance, a username, and a password. And so if you're using the CLI to try to connect to a database, or if you are, say, executing a JavaScript or a Python file that lives inside of one of these project directories, our bindings and our CLI are smart enough to know where on the file system to look for those credentials. So you don't need to pass in credential information manually. You don't even need to set environment variables. It's able to kind of auto-discover those in a development environment. And so just to prove that that's the case, go ahead and run just the EdgeDB command here, which opens up the REPL. And we are now in an interactive terminal that's actually can execute queries on our running database. But currently, we have a problem, which is that there's no schema in our database at all. So we can't actually create our to-dos. Something to point out here is there's one other thing that the EdgeDB project init command does, and that is it creates a couple files. It creates the EdgeDB.toml file. This lives in your project root and is sort of a configuration file for the EdgeDB project. If you haven't heard of toml files, they're a configuration file format that's really common in the Python ecosystem. And currently it just stores a single setting, which is the version number of EdgeDB that this project is meant to use. It also created this DB schema folder here. Let me make this a little bigger. It created this DB schema folder, which contains a default schema file, which is where we're going to actually be writing our schema. Schema files are defined in ESDL files. And then we also have this migrations directory, which is currently empty because we have no migration history. So let's get started and start writing our data model here. It's going to be real simple, just a single object type called to-do. That's going to contain a required property called title, which is a string, and a required property called completed, which is a Boolean. And just to make our lives a little easier, let's just assign a default property of false to that, because normally when you're adding a to-do list, to-do onto your to-do list, it is not already completed. So I think it's safe to assume that the completion status would be false by default. So now that we've got our file written and saved, we go ahead, jump in and run EdgeDB migration create. This actually reads in that default.esdl file. And in fact, you can split up your schema across multiple files if you want. It'll stitch together all of the whatever.esdl files inside of your DB schema directory. So you aren't stuck with a several thousand line long schema file, which I don't know about you, but I've done that before, not fun. The great thing about the EdgeDB migration system is that, well, there's a lot of great things about it, and I'll talk a little more about it in my second talk about ORMs specifically. But when you create these migrations, you're in this interactive tool here, where it presents all of the detected changes to your schema in an interactive way. And you can kind of sanity check them here. There's just going to be a single question, which is, did we create this new object type? But it's really one of the most impressive features of EdgeDB, which is that you're actually in conversation with your database while these migrations are being generated. The CLI, it doesn't generate the migration logic. It just takes those schema files, kind of shows them to your running database server. and then ask the server, ask the database itself to figure out how to modify its current schema to something that conforms to what's defined in those files. So we've created our migration. You can see here that we now have a migration file inside of the DB schema directory. This is the DDL, which is data definition language, which is sort of the foundation on which SDL is built. To actually execute that migration, we run EdgeDB migrate. And at this point, we are off to the races. We've got our running instance, we've got our schema locked and loaded, and you can actually see here that we've got our to-do type all loaded into our database. In fact, we can quickly, just to show that this is working, insert an initial to-do here. Whoops. There we go. Just to prove that that's working. So it generated the to-do with this unique identifier. So let's go back, restart our server here. Now that we're able to create to-dos, we actually need to implement our database logic. And so that means we're going to be executing some queries. So let's go ahead and install the EdgeDB module from npm and pop into our API file. Actually, there's a couple files here. There's a single big React component here, which is actually the front end code that you're seeing over here. And then we have an API route, which is the Next.js concept for basically just any sort of HTTP server. So we've got these endpoints here. For simplicity, we're implementing them all in a single file. And so these are the endpoints that we're going to end up implementing. We've got a get endpoint that fetches all the to-dos in the database, a post to create new ones, and then a patch which toggles the completion status of a particular to-do. So since we have the EdgeDB module already installed, the kind of older way to do it, or at least up until today, the way that this would be done is you import the create client function from the EdgeDB module, call that function to instantiate a client. You'll notice, like I mentioned, no arguments required to this. We're using the EdgeDB module here, and it's able to auto-discover the credentials of that linked instance, the instance that's linked to our current project. And if we were doing this demo yesterday, what we would do was just basically start calling the queries on this client, passing in some EdgeQL to execute, and that would be the way to run these queries. But this is now, and today is the first public announcement of the EdgeQL query builder for JavaScript. So that's what we're going to use. It's real simple. From inside your project directory, once you've got your schema set up and you've installed the EdgeDB module, just run npx EdgeQL.js. What this does is it introspects the schema of your running database and generates basically an textbook version of all EdgeQL. So you can represent any EdgeQL query you want, all with EdgeQL, with TypeScript code. So that generated some files, as you can see over here. Again, this is in the DB schema directory. And here there's an EdgeQL.js subdirectory with a bunch of files in it. That's where we're going to be importing the query builder from. And the way to do that is import E from, we're in a nested route. So from DB schema /EdgeQL.js. And just for a quick teaser of what this E object is, basically every type, every function, every operator, every statement in EdgeQL is reflected somewhere on this E object. We're going to be going into more details in a future talk, breaking down how to use this. For now, let's jump in and actually start implementing these endpoints at long last. So we're going to be writing a query here that is equivalent to this EdgeQL. So we're fetching all of the to-dos, that's wrong, plus their title ID and completed status. So const query, we're going to be doing a selection. So e.select, e.to-do. And then to actually specify the fields that we like, we use this closure here that returns an object. And then this object is what we use to specify the properties we want, among other things. And we'll be going into details later. Okay, so we've got our query written. Now all we've got to do is actually get some results back. The way that we do that is with the run method that exists on every query builder query. And it accepts a single argument typically, which is a reference to our database client that is actually going to be used to execute this query. And now let's get rid of this hard-coded data. Almost forgot, and await query.run is, of course, returns a promise that returns your data. Let's see if this compiled. It did. And now refresh the page here. Okay, there you go. This is the initial to-do that we created from the REPL a while back. You can see nothing else is implemented yet, but we are actually fetching to-dos from the database. Let's jump in and start implementing those mutations as well. The first one is this insertion, which is going to be a pretty simple e.insert, e.to-do. And real simple, we just pass in the title that we're going to pull out of the request body. And then let's go ahead and just, this query doesn't need to return anything. So we're just going to do await query.run client because it's an insertion, and then change these status codes here. So now that we've done this, we should be able to actually start creating some new to-dos. Let's see if that's actually true. Still compiling. Second to-do. There you go. There we have it. So we've got our insertion endpoint working. And now jumping into this last one, which is the most complicated. It's an update query, as you see here. We're going to be actually applying a filter for a particular to-do, and then we're going to be using, we're going to be just toggling the value of that Boolean completed field. So e.update, as you might expect, we're updating to-dos, and we're going to use that same closure syntax. Inside of here is where we specify filters on what we actually want to update. Now, we need some way to reference this ID property. In EdgeQL, because we're inside of this update to-do statement, we're able to use the leading dot notation that Victor mentioned. So basically, we can refer to the ID or the ID of the to-do that we are updating here. We're in the scope of to-do, so we can reference its properties and links with just this dot notation. In TypeScript, how are we going to be able to represent scope? Well, we're going to use functions. And in case you were wondering why up here, this selection here is an object, rather a function instead of just a plain object, it's because inside of these functions, we're able to add an argument here that gives us a handle that we can use to reference any sort of properties or links. So in this scenario, we're just filtering based on an ID. So we're going to be using e.op, which is what you use whenever you are using an EdgeQL operator. In this case, the operator we're using is equality. And then the value that we want to pass in here is a UUID literal. And we're going to just be passing in this ID variable, which we pulled out from the request parameters up here. This is still throwing us an error. That's because we need to tell it actually which fields to update here. And we're going to be updating the completed variable. We're going to be using another EdgeQL operator, in this case not, so e.op not, and then we just pass in to-do.completed. So this query here is is precisely equivalent to the EdgeQL we have up here. Let's go ahead and execute that as well. Query.run client, change the status code, and see if this works. Compiled successfully. And we can now check off these to-do items, which is fantastic. So we've got a fully functional to-do app here. We can create new ones and actually mark them as complete. This was a pretty brief overview of kind of the full set of developer workflows, everything that you are likely to touch over the course of building an application from with EdgeDB, all the way, from our CLI to our actual client libraries, and now the query builder as well. If we actually were going to be deploying this to production, we've got a bunch of deployment guides that are available on our website for actually hosting EdgeDB. Let's make that bigger. Under guides here in the sidebar, and then deploying EdgeDB. So lots of options. We are also working on EdgeDB Cloud, which is something that Yury will talk about in a later talk, a hosted version of EdgeDB. And of course, to explain a little more about this EdgeDB project concept, it's primarily intended for development use, just so it's real easy for your CLI to use the CLI or our client libraries in a way without having to use a bunch of environment variables or specify connection information, since that's always a drag. In production, though, you would use some sort of environment variable to actually tell your application how to connect to the production database, just to explain how this might look in a production environment as opposed to development. Okay, I'm gonna stop the share. Hopefully that's a pretty decent overview of how to build things with EdgeDB. I'm going to go ahead and publish an updated branch to that repo as well, so you can see the completed version of the code and run that if you like. All right, I think Sully was potentially keeping an eye on the Discord about FAQs. Not sure if there are any.
Yeah, so one question from Discord is the query builder really auto-completing things based on types from the schema?
Oh, why isn't it? It sure is. And we're going to go way into that in my talk later, which is ostensibly a talk about ORMs, but is really me showing off the query builder for a little while, since it really is beyond anything you've ever seen. But yep, as you can see here, let's say we're inside of just this select call here. It knows that we're in the context of this to-do type. So you can see everything that it wants us to, that we could put into this object, which is, any of its properties like completed or title. We can add filters, order bys, limits, offsets, and I'll get into this a little more later, but let's say we want to fetch the title of this thing true. And something, well, okay, let's fetch the title of it. And then just for fun, let's also compute an uppercase version of the title. We can drop in this to-do reference in the function there, and then just use any of EdgeDB's built-in functions, e.stirUpper, pass in to-do.title. And now the result of this, if we come down here, is an array of objects that contain not just the title, but this uppercase version of the title as well. All fully full type inference for every result coming out of any query builder query. And we're going to be talking about it. Don't worry.
All right, that's really exciting. And there seems to be a lot of excitement about the query builder, and I'm sure people will love to hear more about it in about 20, 30 minutes.
They're going to have to cut me off because I will talk about the query builder all day if they let me. Awesome. Thank you, Sully.
All right.
Next up, we are going from how to build apps with EdgeDB to how EdgeDB is built. So we're going to be hearing a talk here about some of the architecture of EdgeDB to hopefully answer some questions for the very technically minded among you. So it's my pleasure to introduce you to the senior software engineer and diagram aficionado of EdgeDB, Fantix King. Take it away.
Thank you, Colin. Hello, everyone. My name is Fantix. As Colin mentioned, I'm a software engineer at EdgeDB, but I'm usually known as being too obsessed with diagrams. So I'll mostly talk about the architecture of EdgeDB today with some real diagrams. So you are warned here. Just a quick disclaimer. In the Discord channel, I think people mentioned Gino. And yes, it is an ORM library I built, but its full name is actually Geno is not ORM because I really hated ORMs in general. All right, getting back to the talk. On 30,000 feet above, EdgeDB itself is actually pretty easy, the architecture. Here you have a client, you define a schema as demonstrated previously, and you issues a bunch of EdgeQL queries to EdgeDB. On EdgeDB side, it compiles your EdgeQL queries into SQL queries and execute them in the Postgres cluster. In this cluster, we store all the data, including the user data, as well as a bunch of built-in data like the built-in schema, data types, standard library roles, configurations. All that is needed to run a proper EdgeDB instance. EdgeDB usually comes with a bundled Postgres, so this whole thing is encapsulated and you have no feel of the Postgres cluster in most of the cases. But in the following diagrams, I'll show them separately so that you can see actually the interaction between them. In this chart, we can see more internals about EdgeDB server. The server itself is written in Python. We also built a lot of Python and Rust extensions to make the critical parts really run fast. EdgeDB server uses UV loop to handle all the I/O on the network and uses a subprocess pool to compile the EdgeQL queries. The compiled SQLs are stored in an in-memory cache, as well as the prepared statement from the Postgres, so that when the same EdgeQL query is issued again and again to the server, it will just try to load the cache and run the execution directly. Like async.pg, EdgeDB server is also using the Postgres native binary protocol to talk to Postgres in a very fast way. Because we, as in the middle layer, knows all what we need to do with the backend Postgres, we did a lot of optimizations on the network, is like pipelining, so that literally every, like Yury mentioned at the beginning, every EdgeQL query only issues one network packet to not only the EdgeDB server, but also to the Postgres, and it returns the result. Similarly, between EdgeDB server and the client, we designed a binary protocol for the communication, and this is intentionally inheriting the same binary data format as the Postgres binary protocol does, so that the EdgeDB server itself will don't have to do any unpacking or reserialization of the actual data. So altogether, it looks like this. The client issues a EdgeQL query. When the server is fully heated, it just loaded all the cache and run the query directly in the Postgres cluster, and it returns the binary result with the Postgres headers. We parse the headers and don't touch the binary data, and rewrap it with EdgeDB headers, types, and etc., and just send it over back to the wire. So everything is just fast and simple. We're literally talking about microseconds of latency added by the EdgeDB server itself. When it comes to a more realistic production environment, things becomes much more interesting with more clients. They're having more connections to the EdgeDB server, and these connections all share the same cache we mentioned earlier, as well as a Postgres connection pool here. That literally means the connection between clients and the EdgeDB server is super lightweight and completely stateless after the authentication. So, also because EdgeDB server is driven by UV loop, we can easily scale the number of client connections to tens of thousands or even hundreds of thousands of connections, because those connections will only acquire a Postgres connection from the pool when they're issuing a query, and they will return it back to the pool as soon as they finish the query. The same thing applies to transactions, but during the transaction, the Postgres connection will be pinned to the client connection, and likewise, they'll return as soon as they are the transaction finishes. This is very likely to be the PG bouncer mode. In this case, you can just use a single EdgeDB server without any other abstraction layers to make your application happy. You might also have noticed the two databases here and our two groups of clients. This corresponds to the concept in Postgres where you could have multiple databases in the single Postgres cluster. And EdgeDB supports the same concept, only that we added more optimizations to this model because EdgeDB server actually knows whatever each client here tries to do with the data. We can, that makes us able to implement a rather complex algorithm in the Postgres connection pool so that we can balance between the different pressures from different clients so that none of those quiet clients will be waiting for a connection for too long time while the other group is busy with the very frequent queries. Okay, that is what we did to the server side quality of the service. Now let's switch gear a little bit to the front end, the client side. When you are building your application, you are usually dealing with the real world, which is full of unreliable factors. Like you might have the cloud, you might have HDB server in a Docker container. You might have a virtual network in between them. Anything that might go wrong will eventually go wrong, Murphy's law. So usually your application is taking care of all those network or unexpected events. But in this case, HDB official client libraries is taking care of part of the issues for you. Like we're automatically retrying to establish the connection under your configurable retry policies. Once the connection is established, the HDB binary protocol is also defining a hierarchy of errors. Part of them is the retriable error that is defined in the HDB server side to reflect errors like a transaction isolation level serialization error, or it's simply the Postgres cluster is temporarily unavailable because AWS is doing some failover on it. In this case, as HDB server, we know exactly what happened. We know it's safe to retry, so we propagate this retriable error to the client library, and it will just retry it for you. Same thing for network errors, only that we're doing it on read-only errors, and we know that from a two-phase interaction between the server, and in which we also cached it to make the round trips a minimum, because on the second time there will be only one optimistic query. I won't get too deep into this, but I would also like to mention when this whole retry logic comes to transactions, it becomes more verbose. As you can see here, this is a snippet of Python code. This is the same transaction in JavaScript. The HDB client libraries are enforcing using this kind of for grammar the users to think about the transactions, because we think that is the right thing to do when the transaction is facing some retriable errors. You should simply retry the whole transaction block instead of just a single query. And in this case, from grammar level, you as a developer will think, what should I include in this transaction when it is retried? This is, what we did for the overall quality of service on the client side. From a different perspective view, HDB itself is not just a server. As we mentioned multiple times, we are building the same retry logic and quality of service into several different client libraries so that you will have the consistent developer experience using different languages. EdgeDB itself runs on different backend Postgres clusters, and we especially have a CLI command line tool you have already seen previously. We're super proud of it. It delivers the same developer experience and conventions and workflows on your favorite development platforms. Our website is maintaining tons of learning resources, and for the quality assurance and the continuous delivery, we're automating everything on our development, on the core development. We have thousands of automated tests running on about 100 different combos of environments. We're automatically releasing to about 60 different targets that you are downloading and installing on the client. And in the future, for production usage, we have this upcoming EdgeDB Cloud, which I won't spoil too much in my talk here. All right, I think that's all I wanted to share here. Thank you very much. Back to Colin.
Awesome. Thank you, Fantix. We have a comment here on the Discord, which is, he wasn't kidding. These diagrams should be framed. So you officially have the seal of approval of the Discord, and I completely agree. A quick question as well about, you briefly alluded to an algorithm for doing some connection balancing if you have multiple clients that are, say, using different databases inside of a single instance. Could you talk a little bit about how that works?
Yeah, sure. I can quickly go through that. It's basically an algorithm to balance between the not so busy clients with the busy clients when overall the EdgeDB server is under a full stress. Because if it's not fully used, the connection pool can be all allocated to all the usages. But when there's a computation, we cannot simply allocate all the backend connection pool, Postgres connections to those who are requiring for connections a lot. We're balancing between like execution time, latency, and frequency, and so that all the clients, no matter they're just ad hocly sending queries or they're issuing requests very frequently, they will have a relatively equal opportunity to get a connection and run. So there's no starving. That's basically what we did there. I hope that answers the question.
Absolutely. Yeah, thank you, Fantix. And yeah, I can honestly say almost everything I know about the compiler, I first learned from one of your diagrams, so keep it up. We're switching back to a slightly more practice-heavy topic here, I suppose, away from compiler land and back to something that many of us have used, which is, of course, the topic of object relational mapping libraries, specific and how that kind of where EdgeDB kind of stands in relation to them, specifically how they may or may not be actually necessary anymore. So let me share my screen and pop into these slides here. So this is a farewell to ORMs. As it happens, the design of EdgeDB, as we've sort of arrived at it, has ended up essentially replacing everything that ORMs can do. Everything that ORMs can do, EdgeDB can do it, and it can do it better as well. And it can do more things too. It's really a pretty conclusive battle here. We're going to talk about a few major pillars of functionality in ORM libraries. Firstly, schema. Kind of the first thing you do when you start using a new ORM is to actually use some sort of syntax to declare typically an object-oriented schema. Migrations. So this is not true for all ORMs, but many of them these days try to be the single source of truth for your application schema. That means that they have to have some concept of migrations in order to actually let you evolve your schema. And finally, they've got some sort of API that lets you do typically pretty basic CRUD operations, and if you're lucky, some aggregations and grouping as well. So here, we're going to be using Prisma as sort of the point of comparison. It's a TypeScript and JavaScript ORM. Actually, something that you'll notice here is that they actually define their own data schema definition language. So this is using their schema, their Prisma language. You're actually able to generate clients, I think, in a couple different languages now. So this is a really basic sort of user blog post schema. As you can see, both user and post have a required ID property. We've got an ability to fetch the posts of a given user and the author of a given post. This is what the equivalent schema looks like in EdgeDB, in our schema language. And there's a few things to note here. Yes, EdgeDB's schema is dramatically more concise. There's a couple of main reasons for that. We don't need to include that ID property. That's one of the fundamental design choices that EdgeDB makes, which is every object in the database has that required UUID property with a uniqueness constraint right out of the gate. And because we know that every object has that ID, we don't need to futz around with foreign keys. We can just say, this object has a link to that other object. We know they both have IDs, and we know under the hood how to actually store that. Prisma, on the other hand, you specify this posts relation, which is how you fetch the posts of a given user. And then we have this this author link, which is how you fetch the author of a given post. To their credit, Prisma is sort of implicitly acknowledging the limitations of the abstraction that they can provide here. And they do that because you still need to specify this author ID field. They don't want you to have too much distance from the underlying data model as it's represented in SQL, because they know that there's a lot of things, a lot of queries you can't represent with Prisma's CRUD API. And so they actually have you specify that author ID foreign key and then use this @relation directive here with a couple of arguments to sort of wire everything together. All of this goes away when you just commit to the graph-relational schema in the way that EdgeDB does. Now, that shows how EdgeDB can do the same things as ORMs in terms of data modeling. But of course, it can also do dramatically more, things that you could never really conceive of in any sort of ORM that we're aware of. And the crux of that power is simply this. Inside of your ESDL files, where you're defining your schema, you have access to the full power of EdgeQL. It's all there. In fact, SDL is a superset of EdgeQL. So you're able to write entire queries inside of your schema. And there's sort of a gut reaction that certain longtime ORM users have about computed properties, stored procedures, things like that. In the context of the workflows that you typically see with SQL databases, that makes a lot of sense. If you don't have some canonical representation of your schema that is declarative and that you can read, then yeah, you end up in this weird situation where it's difficult to know what computed properties have been declared, what stored procedures are in your database, because your schema is basically smushed across a bunch of SQL migration scripts in a lot of cases. You're not able to just see what the current state of the schema is and read it. It's like if you were trying to write a program and you had to, exclusively write your code as a sequence of git diffs or something. That's sort of how it feels to kind of mentally track your schema in SQL in a scenario where you don't have a declarative schema. So let's just quickly run through some of the things that you can do when you're modeling your schema in EdgeDB. This is pretty simple, another blog post type here. But we're actually in this required property title, we're adding in a custom expression that actually makes use of one of EdgeQL's standard library functions. In this case, one for actually doing regular expression testing. So we've got this first argument here, and then we pass in the first letter of __ subject, which is just a way to reference the property on which this expression, this constraint is defined. So what this does is it enforces that the first letter of our blog post title is capitalized. Let's take that another step further. We can declare constraints not just on individual properties, but also on objects as a whole. So here we've still got that title property, we've got a published property, and an optional content property. The reason it's optional is when you first create that blog post, let's say our application has a form where you type in the title of it and hit, create blog post, and then it pops you into an authoring interface. Initially, you may not have any content there. But we want to make sure that the user doesn't accidentally publish a blog post that doesn't have any content in it yet. So what do? We actually add a constraint onto this entire object type. So one of two things has to be true. Either content has to be there, or the published has to be false, which means that you can no longer have a blog post here that's both published and lacking content. If that's possible in an ORM, I haven't seen it, but if it is, actually let us know in the Discord. Another thing here, we're showing off computed properties here. We've got that same blog post with the title, and we're actually generating this slug, which is what's going to be used in the URL of our hypothetical blog CMS here. So we're going to take that title. What this stir lower function does is, as it sounds, it takes the title and converts it all to lowercase. And then we're going to be using a regular expression replacement function to take everything that isn't just alphabetic character and replace it with an underscore. Not only that, once we have this defined, sorry, that's the formatting change there, but it's the exact same code for that property slug. Now, what we can do is just add an index on that computed property slug. A pretty common thing we're going to be wanting to do is pulling a slug out of some URL of an incoming request and quickly looking up the blog post that it corresponds to. Well, we can do that now entirely with this computed property, and that query that we run is going to be really fast because we'll have fully indexed on the slug of all these blog posts. Of course, there's other things like Victor mentioned in his talk, which is we can have links between different types and can actually traverse those links in the forward direction or the backwards direction. And there's no special API here for declaring the backlink. It's just a computed property like any other. We're using EdgeQL syntax here. We're using that expression and kind of assigning it to this computed blog posts link. And there's no, we're just using the primitive concepts that EdgeQL gives us and using them in our schema to do things that are complex or useful, such as the ability to traverse these links in the reverse direction. And of course, we have the ability to have abstract types, full schema mix-in support in EdgeQL, which in scenarios like this one, let's say we want every blog post to have a comment section, and we want actually a hierarchy of comments where each comment can have comments. That is preposterously easy to do in EdgeQL, and it's preposterously difficult to do in a lot of other scenarios with an ORM. So that's the quick rundown of schema modeling. This didn't even get into, I'm just realizing the concept of link properties, which Victor alluded to. Because we've got that graph-relational model, we can actually attach properties to our links, which opens up a whole new universe of ways to model data. Okay, but moving on to migrations. There's really two options that ORMs have. They can either actually try to be that single source of truth, like I mentioned, and have a migration system, or they could not. Either way, you kind of lose. If they roll their own migration system, there's no standardization to it. They have their own way of representing migration files in their own workflows for creating or executing them. And you end up with a very fragmented experience. If they don't do migrations, then you're also kind of stuck because you've got to use yet another tool to write your SQL migration scripts with ups and downs and executing those, and you end up with another layer of complexity in your stack. Of course, the root of this problem, of all these problems, is that SQL doesn't have a first class citizen concept of a migration. Well, that's not true in EdgeDB. In EdgeDB, every migration you execute is automatically tracked by the database. The actual migration plan itself is generated by EdgeDB, like I mentioned in the live demo. You basically write your schema on your local file system, and when you run EdgeDB migration create with the CLI, it kind of sends those files up to the server, to the database, and it figures out how to actually modify its own schema. And yeah, there's an official workflow. We've got the CLI. You run these commands, and it's the same everywhere. It's the same no matter what language you're using or what framework. It's just a unified developer experience all the way down. And now let's jump into the actual APIs here. This is really the meat and potatoes of why ORMs exist and where they really provide value. You can kind of summarize, I'm trying to summarize what ORMs really do in terms of functionality, what sort of functionality they provide, as concisely as possible here. This demonstrates a pretty simple query. You're fetching some movies. You're able to add some filters onto that query. Here we're filtering based on the title. You can tell it what fields you want to select. In this case, we're selecting titles. You can nestedly fetch related properties. In this case, the movie.actors, which is a massive win. We're certainly not denying that ORM libraries solve real frustrations and problems that people have. One of those is writing any sort of nested query and having to deal with join syntax in SQL. That's a problem that ORMs have solved pretty conclusively. So we're able to actually fetch those related actors, and then we can also add some additional filters even on those related objects. And there's going to be some sort of create, update, delete function. Some of the properties of what these APIs share across all ORMs, they're code first. You're writing your queries not as strings, which is common in SQL. You're writing them with code, which is inherently desirable for a lot of people. They're object-oriented. You can fetch that nested actors, those related actors for a given movie, no joins required. And it's idiomatic. This means different things in different languages, but in the context of say TypeScript, that means that you're getting back a strongly typed result from your queries without having to separately declare the static representation of your query result and a runtime version of your query as well. Now, we're going to be talking about the query builder as promised, and I'm going to be explaining how you can essentially match the functionality of what you do with ORMs, and then quite a bit more beyond that. So I'm going to go ahead and switch over to a little demo environment here. So this is going to be a demo environment that contains a movies data set. You'll see which movies here in a second. Sorry, I kind of forgot to do this bit. Okay. I also have a kind of front end here so we can kind of see what's going on. That's just another simple application, which I'm going to open up right here. I can localhost again. All right. And then I'm going to open up the actual code. So here's the queries that we're going to be writing. Sorry, should have done this before. We're going to be writing queries inside of this query.typescript file here. And this is actually, all these queries are going to be relying on the schema that Victor built up in his talk, which is that Netflix schema we were referring to. So we've got a person type. We have an abstract content type that's extended by movies and TV shows. So let's jump in and write some queries. A question that you'll get a lot when you start building a query builder and saying things like, we're killing ORMs, is what can you represent that ORMs can't? A lot of times the temptation is to go into the real complex stuff right out of the gate. And we are going to do that, but I will give you, here's one that you can't represent in any ORM that I'm aware of, which is just selecting the literal string hello world. And this is sort of an interesting point here, which is that because we are a query builder, we represent the semantics of EdgeQL pretty faithfully. EdgeQL has a whole type system. It has a whole concept of sets. It's got lots of operators. All of these basic elements of the type system, this is a very thin layer on top of EdgeQL. So we still have representations of all of those. If you know EdgeQL, you can actually learn the query builder really quite fast. So e.select hello world, you can see that we are writing this query, executing it, and returning the result. That result is going to show up over here just in a JSON format. Let's see what else we can do here. First, we can start using some operators. So instead of just hello world there, let's use one of those functions we saw earlier in this talk, string upper, and see what we get from that query. It uppercases it. Now we can look at using some operators as well, which is another thing that you saw in the to-do talk. So let's go ahead and try, let's see, maybe hello world. I like, which is a type insensitive like operator. And then we can just check if the word hello shows up anywhere in there. And that should return true, false. Okay, whoops, that should be a percent. There we go, true. Something to note here, as you can see, the result here is now a Boolean, which means that we're actually inferring the type of this EdgeQL expression here. It knows that when you do, some string, I like some other string, the result is going to be a Boolean. Whereas if we do something else, say 2 plus 2, whoops, 2 plus 2, then yeah, it's going to know that that result is a number. But if we switch this to 2 greater than 2, well, it's back to a Boolean. Every query I write here moving forward is going to be strongly typed, and that type will be fully inferred by the query builder itself. All right, let's move a little beyond this simple literal stuff and select some movies. So e.select e.movie. This is represented precisely as the EdgeQL query select movie. So just as with that query, by default, it just returns a big list of IDs to us, like so. That's not super interesting to look at, so let's go ahead and fetch some properties on there as well. So title, true. And we've got every single MCU movie. Yes, I did spend solid 2 hours last night populating a database of Marvel movies. That's how I chose to spend my time. So we're fetching that title now. Let's add a filter to it. And because, as I mentioned earlier, if we're going to be doing something like filter.title equals the Avengers, we're going to need some way to actually reference this title property. And again, the way we do that is we actually add an argument into this function that we're passing as the second argument to e.select. And then we can just do something like e.filter. We're going to be using an operator like we used before. Get full autocompletion here on all of the properties and links of that movie, equals, and the Avengers. Something to note before we run this query. Note that the query results that we're looking at from before are an array of objects. Now, when I run this query, save, run, you see that the result is actually a single object. That's one of the most interesting and hardest to implement parts of this query builder, which is it knows that this title property here has an exclusive constraint. That means that only one movie in the entire database can have the title of the Avengers. So what it does is it knows that this expression here is an equality expression. It's checking for the equality of an exclusive property with some literal value. And it knows that when in that particular situation, it infers the cardinality of the results, just as EdgeQL does as well. If we change this away from equality to something like I like, which could match potentially many movies in the database, you see that the result is now back to being an array. And indeed, this changes to an array as well. All right, so let's switch back to just fetching the Avengers and start looking at some nested fetching. This is all definitely in the domain of ORMs currently. So we can go ahead and pull in those related actors, just like we did before, and their names. Return that. And we've got Avengers with its full set of actors there. Here's something that's a little trickier, or at least less pretty, less pretty to do with ORMs, which is we can fetch that character name as well. Since that is, we can just track that as a bit of metadata on the link itself. Another thing, we can add in these computed properties, which I mentioned a little bit in the FAQ section from before. So yeah, something to point out: title and actors, they get auto-completed because it's a link and a property of the movie object respectively. This filter key also gets auto-completed. In fact, you can see there's a few operations we can drop in, like filter. We can do order bys. We can do limits and offsets as well. But you can actually put anything you want in here in these other keys as well. So let's do uppercase title, and then we can just drop in really any EdgeQL expression that we want. So let's do string upper movie.title again as a demonstration of this. And you can see that in addition to the Avengers up here at the bottom, we've got the uppercase version of Avengers. This is extremely useful to be able to put in any computed property you want into these queries, and they can correspond to an arbitrary EdgeQL expression. In fact, we can, this can be truly whatever you want. You could just, try. I'll try to limit the scope of these examples for the moment. Inside of this nested fetch that we're doing here on actors, currently we're just using this as a simple nested object, but inside of each of these links, we're able to write that also as a function, which means we are able to get a reference to this actor variable here. So if we wanted to do things like filter the list of linked actors by, say, the name, actor.name, I like Chris, then we can see that we're going to limit the results of the fetched actors. Let's see here. Actor.name, I like Chris. Oh, there we go. No one. Oh, right, forgot my parentheses. There we go. There we go. Now we've got our two Marvel Chris's showing up in that link. Now, this is all fine and dandy. Really, where this starts to shine is with the composability of queries that you write with the query builder. So let's go ahead. If you notice here, when we look at the characters in the Avengers, we don't currently have a reference to Thanos, which, as we all know, showed up in the post scene of the Avengers. So that's got to be in here somewhere. So let's go ahead and switch gears here. We're going to be switching away from selections and actually inserting a new person into the database. So e.insert e.person. And that name is going to be Josh Brolin, the actor who plays Thanos. So this is an expression that now corresponds to an insertion query. Of course, we also need to now get the Avengers back. So we're going to be updating it. So const updated Avengers equals e.update e.movie and we're going to be adding in that filter, e.op movie.title equals the Avengers. So this is going to be the set. This now defines the set of objects that we're going to be updating. And then we use the special set key here to actually provide it which links and properties we're going to be setting. We of course get auto completion here as well, and all the things we can update. In this case, we're going to be updating actors. Now we could just do actors : Josh. What this would do is actually overwrite all of the actors that are linked to the Avengers. And so we'd lose all of these other characters that are currently there, like, the whole Captain America, etc. So what we actually want to do is just append to the set of linked actors. We do that with the plus equals operator, and then we're going to pass Josh in there. So let's go ahead and see what the result of this looks like. It's going to be pretty lame. Namely, it's just an object with an ID property. That's because by default, update statements in EdgeQL just return the ID of the object or objects that you updated. So I think it would be fun if we actually put in a query here where we would actually select some properties on this updated Avengers object. So we're going to do updated Avengers. We're going to pull in the title. And then as a demonstration of computed properties again, we're going to do Avengers dot actors dot name, which is a path like Yury talked about. And what this will return is just the names, a set of names corresponding to the actors that are in this particular movie. And we can see the inferred type there is we're going to get back an object. It's going to have a title and an array of the actors' names. Let's go ahead and save that, run this. And it failed. Excellent. Live demos for the win. Okay. Let's try. I think I must have. Let's go ahead and make this a little easier on ourselves and just fetch the actors link and the name property. Scope does not exist. I'm gonna quit the server. Sometimes it can get a little confused with all the hot reloading I've done in this talk. So we were updating Avengers, passing that into select, and then selecting some properties on it. Interesting. Okay, well, this is a tricky one, folks. Oh, well, all right. I guess it doesn't like fetching actors. So yeah, in case I didn't mention already, the query builder is in beta as of today, and we're going to be looking into this one. So as you can see, when you're writing really complex queries like this, it really starts feeling like you're writing a script, like you're just writing TypeScript code that can do updates and inserts and selects and deletes, and you can just kind of compose them all into a very complex single query that does a lot of different things. In case it wasn't obvious, these aren't executing separately. We're not running each of these here. There's no await statement. This is just a data structure that refers to an EdgeQL query. And we're taking that subquery, we're dropping it into this one. And then we're taking updated Avengers and we're dropping it into that final select. All of this actually compiles to a single EdgeQL query that gets executed all in one go under the hood. In fact, we can actually see what that, oh, sorry, we can't do that. You can see with any given query what that generated EdgeQL is going to look like by calling the toEdgeQL method right there. So this is totally transparent. You can see exactly what's going on if you want inside of the query builder. And that's something that we think is very important, and that is going to really unlock a lot of potential in terms of the developer experience. the great thing also about this is the reason we're able to provide these sorts of amazing APIs is because we're compiling to EdgeQL, which is just an amazing target for building sorts of idiomatic APIs in different languages. EdgeQL, because of that graph-relational nature, it fits cleanly into object relational languages. So it's really been a remarkable project working on this query builder, and I'm very excited to see what you guys build with it. I'm gonna stop the share now, and Sully, were there any questions coming in from Discord? You're muted. I think you're still muted, unless this is a problem on my end. I cannot hear Sully. Sorry.
Somebody asks, when are we going to get this sort of thing for other languages like Python and Go?
Oh yeah. Well, that's a top priority for sure. We're planning to build query builders for all of the languages that we have a client library available for. So that's Python and Go, like you mentioned. We're building a client library for Rust from there. In terms of query building capabilities inside of Rust, we're going to need to do some thinking about that. But yeah, we're excited to bring as close to this sort of experience as possible to the other languages. Of course, TypeScript is in a league of its own in terms of the flexibility of its type system and what you can do with generics and inference and auto-completion, things like that. So all those are coming soon, and we're going to continue investing in the TypeScript one for sure, including fixing whatever that darn bug was. So yeah. Awesome. Thank you, Sully. I'll take over again and immediately hand right back to you, I'm realizing, for the penultimate talk of this event, back into compiler land. So you're already here, but I'll just say you are Dr. Michael Sullivan, recovering academic. You work on the EdgeDB compiler, and you're going to tell us a bit more about how EdgeDB compiles queries and how it plays nice with Postgres. So take it away.
All right. Hi, everyone. Like Colin said, I'm a recovering academic. I've got my clicker from my thesis defense, which is hopefully good luck. I'm going to be talking about compiling EdgeQL, which is subtitled Standing on the Shoulders of Giants, because we think we have, with EdgeDB and EdgeQL, seen a little further than others. And we think a lot of the reason we've done that is because we're standing on the shoulder of a giant, Postgres. So I'm going to talk about three main different things as to how EdgeQL and EdgeDB leverage Postgres. First, schema mapping, how we map our notion of a schema, which has been discussed a bunch in previous talks, onto a Postgres SQL schema. I'm going to talk about query compilation, how we take an EdgeQL query and turn it into a Postgres SQL query. I'm going to talk about why Postgres. Why did we build this on Postgres instead of on MySQL or SQL Server or Oracle or Mongo or something. So first, schema mapping. The heart of it is types. The heart of EdgeDB databases are object types, and every object type is represented with a SQL table. For every object type in your schema, we will create a PostgreSQL table. But just that's not that interesting. We want to talk about what goes into that table. So like we talked about, one thing that goes into all of them is an ID field. But on top of that, we want to put in all of the data that was declared in the schema. So the most basic sort of data that might be on an object is a single link or a single property that points to 0 or 1 of something else. And this is mapped into Postgres in a pretty obvious way. Every single property on an EdgeDB object maps to just a column in the SQL table. So if we have a property name that holds a string, that's just a text column in the SQL table. Links are very slightly more interesting because we represent links by storing the UUID of the object that's pointed to. So it's just a UUID column. In this case, it's a required link, so it's marked as not null. The most interesting part of this is actually something that isn't here. You might be used to, in some of your SQL schemas, having a foreign key specified here, saying that this is a foreign key referencing the primary key of some other table foo. We don't use that here because we don't need to. EdgeQL queries by construction can't insert or update to point to an object that doesn't exist. And so we don't need to use foreign keys to ensure consistency because it's ensured by the type checker, by the query compilation, by the entire construction of it. And so we get a little performance out of that. In this example, there's one fib I'm telling. The column names here, I've written nice column names. In the actual implementation, column names are unreadable machine-generated things for technical reasons. A little more interesting than single links and single properties, though, are multi-links. And this is because, like a good relational database that stores things in normalized form, we don't want to store multiple links in a single table role. That's not the relational way. The way you're supposed to do it, and the way that Postgres is optimized for doing it, is to create a link table, a separate table that maps as a relation between the source of a multi-link and the thing that it's pointing to. And so when you declare a multi-link like this, we will create a link table that has a source and a target field for the source of the link to the targets of the link. We put a unique constraint on it because all the links are unique, and that helps drive an index. And we also add a reverse index here on the target so that you can go from targets to sources using EdgeQL backlinks. There are a few other things that we do in the schema, and all of them are mostly pretty straightforward. Indexes in EdgeQL are unsurprisingly realized as indexes in PostgreSQL. Constraints are Postgres constraints. Custom scalar types are SQL domain types or Postgres domain types. Type inheritance is a little bit more interesting. So if you remember from our example Netflix schema, we have a content abstract type that has descendants, TV show, and movies. And you could select content and get data from that. The way we implement that is we create a Postgres view that is a union of all its descendants. So we have a view for content that unions together the tables for TV show and movie, including all of the columns that are included in content. That handles things for the select side. When you're doing inserts or when you're doing updates and deletes, which can update or delete things from multiple ones, the view doesn't help us, and we need to do some actual work on the compiler side. But the key idea is we use a view for most of the important queries. So that covers basically all of the details, or all of the most interesting details about how things go into the schema. And so now we're going to talk a bit about how we go from an EdgeQL query to a PostgreSQL query. And the compiler is built in a fairly traditional sort of multi-stage step. I guess I'm fibbing a little here in that I've written two phases. There's really a phase before it, which takes the textual string of EdgeQL and lexes and parses it into an EdgeQL AST. And that's like the first third of any book on compilers. And I just sort of forgot to put it on the phase list because it's also by far the least interesting part about writing a compiler, even though we actually did some interesting stuff on that side, the custom Python parser generator. But the two main phases, as I think about them, are an EdgeQL to intermediate representation phase, where we compile to intermediate representation for our queries that represents data, represents the query in a more simple way, and then an intermediate representation to SQL phase. And we actually have another phase in front of all of that for the GraphQL front end we touched on a bit, where we will convert from GraphQL to EdgeQL, which is another place where we're using, in addition to the query builder, EdgeQL as a target language and having it work pretty well. But so now I'm going to dive into some of the actual parts of the EdgeQL to intermediate representation step. One of the sort of first and most core bits is name resolution. We have a query on the left and a schema that it's referring to on the right, and we need to figure out what each of the names actually refers to. The query on the left is a very simplified version of the Netflix content movie schema with just movies and persons, and title renamed to name for reasons I'll get into in a minute for explanatory purposes. So if we run through name resolution, we quickly figure out that movie refers to the type movie. Actors refers to that link actors. The name on actors refers to the name that's a property in person. And then the name at the bottom of the whole query refers to the property name. And this is all pretty straightforward, except for the one interesting bit, which was how those names got resolved. And that ties into another bit that runs basically in parallel and very interdependent with name resolution of type resolution. And so this is also pretty straightforward to understand. As we're doing it, we figure out that movie refers to a movie, actors refers to a person. And then because we know that actors refers to a person, that allows us to do the name resolution on that name in its shape and figure out that name is a stir. And similarly, this other name, also a stir. The literal dune, unsurprisingly, a stir. And then, since we have to do this for all the pieces in order to verify everything, that whole expression in the filter is a bool. And the most interesting or useful part about this from a user's perspective is that all of this type information, the types of all of the fields in these shapes, that actors is a person and that subshape contains thing name with a stir, all of that gets returned to the client if you're using the binary protocol. And so our clients are able to get a very rich understanding of the data, knowing the types of everything and the names of everything, and can provide a very idiomatic interface in their languages. In Python, even without knowing any of the type information in advance, we get all of the things in the right type and can, provide access just with dot access and everything like that. And a lot of other database clients make it much harder if you want to have the type information. We also do cardinality inference, where everything in the query, we figure out how many objects it might return. So here, movie, because movie is a object that's just a table. It could be an empty table. It could have one element. It could have a million. We infer the cardinality as many, and many means it could be anything. It could be 0, it could be infinite, not infinite. Actors, because it's just a multi-link, also has cardinality many. And then name, because it's a single property and a single required property, it has cardinality 1. If it was single but not required, it would have a different cardinality, at most 1, which means that it could be empty. We also know that name is 1 because it's a required single property. And the literal dune also has cardinality 1 because it's a literal string. But then the most interesting part about this is that we also, because we've done this filter on an exclusively constrained name, because in this example, each movie, we can only have one movie with each name, so there can only be one dune, which obviously is a little counterfactual. There are several dunes and maybe only one worth having. We can infer that the cardinality of the entire thing is at most 1. It may be empty, but it can't be more than 1 because name is an exclusive constraint. And all of this cardinality inference is used to drive the compilation a little and the output format and is returned to the client. So it knows whether there's only one result. It knows for each of the fields how many things can be there. There are a few other things we do. One is scope tree inference. This is not going to be on the test, but core to the semantics of EdgeDB on a sort of theoretical semantics level is that when we have a common path reference in a query, like movie being referred to in 2 places here, unless they're all in aggregates, it gets hoisted out. There's some discussion of this idea in a different forum on our website, but again, it really won't be on the test. more interesting maybe is we do a lot of converting complex constructs to more primitive ones. For example, if we have an array of integers and we want to cast it to an array of strings, Postgres doesn't have a way to do that all at once. So we have to unpack the array into a set, cast the individual elements, and then array egg it back into an array. Maybe more useful is, let's say we have a JSON query argument and want that represents JSON dictionaries or JSON objects that have a name and an age field, and we want to cast that into a named tuple. We translate that into code that calls JSON get with the different fields we're trying to access, and then does the appropriate cast. So name goes to stir, age goes to N64. And a bunch of other stuff lives in this too. We resolve overloaded functions to which of the particular overloads it might be. We inline the code for computed properties and links. We insert implicit limits and type name computations into the queries from the CLI. When you're doing CLI, there's usually an implicit limit so you don't get overwhelmed with data. And we insert type names into the objects we return to provide more useful results. And most of our error checking lives here because the earlier in the pipeline it lives, the better source information we can give about where the problem came from. Next, after that, we have to compile from the intermediate representation to SQL. And so we generate that SQL based on the intermediate representation and this scope tree that we've built that represents that not on the test lifting of common path references. And the compiler is actually structured in a kind of interesting way. We build the query in a way that I will call semi-lazily, in which you have when you have stuff like a object reference and then a shape on it, when we go down to compile the object, we generate code that joins in, a subquery that joins in the tables being accessed, but doesn't add any column accesses to it. And then once we go to compile the shape, we see, oh, we're trying to access these things on this relation we grabbed over there. So now we need to go back in there and add in the column accesses. That sort of builds it up and then pulls the data out later. And then importantly, we serialize all the results into the appropriate output format, which is a good time to talk about output formats. So the main output format we have is a binary format where data is returned as native PostgreSQL types. Strs are returned as text. Int64s are returned as int8s. Object shapes get returned as tuples, and properties and links that have multiple elements, which is one of the core things that we make it easy to do. When you're selecting like the shape of, movie and all the actors, that actors field has multiple elements. We represent that as an array, which will be an array of tuples here. And like I touched on before, the client is returned a type descriptor describing all this output. We also, importantly, have a direct JSON output mode, where instead of this binary format, we output all the data directly as JSON. This is less rich from a client perspective. It's if you're trying to operate on the data from the direct client, it's probably not what you want. But if you just want a really simple, if you want to make a query and then return it from an endpoint without doing any real server-side processing, the JSON mode is a really nice, fast way to do that. You get all the JSON produced efficiently in the database query and don't need to do it on your app server. So that lets us put sort of this all together with a movie query that selects the name and the runtime of a movie and the cast and their names. And approximately the query on the right is what we get. I cleaned it up a little bit to fit on the slide, some of the rough edges. But the nice thing is, even if we generate code with rough edges, Postgres is very good at removing things like an extra select around things. But basically here, the idea right is down at the bottom, you can see us selecting from a movie table, and then we're returning a tuple containing all the fields we want, including in a subquery, we are doing an array egg of, or we select from a link to the cast, joined against persons, and build all that up. All right, so now that I've talked about how Postgres, I'm going to talk about why Postgres. First, an important thing is we target PostgreSQL. We don't target, quote, SQL. And there are a few reasons for that. One, Postgres is an extremely powerful query engine. You can give it complex queries, and it does a great job running them. It has important features like lateral join, and it has them for a long time and well optimized. And in general, targeting one engine allows us to be much better focused. We can take advantage of the one database we're supporting and design something that really pushes it to its limits instead of being spread thin, trying to target the intersection of a bunch of different databases. But even with all that, we push Postgres pretty hard. So one example of a thing that works great in Postgres, but maybe wouldn't other places, is arrays, which we make very heavy use of, both as part of our binary output format and sometimes internally. But arrays are not a universal feature. MySQL sort of has arrays as of a couple years ago, but only in that it has JSON, and a JSON value could be an array of JSON. But there's no way to have an array of integers or an array of tuples. And speaking of tuples, EdgeDB supports ad hoc tuple types, which SQL actually has very poor support for operating on. Postgres is just good enough, and a lot of other databases, I think, aren't, to do things like access an element from a tuple. But even in Postgres, it requires some kind of silly things. To project out of a tuple, we actually pack it into an array, then we unnest that array and read the element out of the column definition list. Though I think Elvis actually had to submit a patch upstream to get that to work. Postgres also has transactional DDL. So changes to the schema can be made inside transactions. Then, of course, since they're in transactions, they can be rolled back if they needed to be. This is really important for a couple of reasons. One, a migration step could fail. You could have some cast in there or some check that fails, and you need to give up and roll back. And it might be possible to implement that ourselves on top of non-transactional DDL, but we really wouldn't want to. But more importantly than that, partially completed migrations shouldn't be visible. If there's a migration in progress, that shouldn't be apparent to any client because the database just isn't in a reasonable state. Unfortunately, lots of other databases other than Postgres don't support transactional DDL, which would make it really hard for us to provide the experience we want for migrations. But separate from that, Postgres is just good. It's a good query engine. It's a good database. The biggest complaint we have about it is that we don't think SQL is really stands up in a modern light anymore. But Postgres still does a great job. And we think that, among other things, EdgeDB actually really helps Postgres shine through. Thanks. So despite hitting the time perfectly in all the practice talks, I went 5 minutes over, but there's no one after me. So Colin, do we have any questions?
Yeah, you thought you did it bad. My talk went, I don't know, maybe 2x over what I thought. I don't even know how that happened. Yes. There was a brief question just about, I guess, the degree to which property names are obfuscated in the underlying representation of the schema and what the thought process behind that is.
Oh yeah, the object names in the generated schema are generally based on the UUID of the object in our schema. So everything in our schema has an ID, and the reason it has an ID is because everything in our schema, the source of truth of our schema is data in an EdgeDB database, right? Our schema is all available in the schema module. You can introspect it all from EdgeDB queries. And so every property, every object, everything in an EdgeDB schema is a EdgeDB object with an ID. And so it's those IDs that are used as the names for basically everything on the Postgres side. And there were a couple reasons for this, but the biggest one is so that things like a rename on the in the EdgeDB schema is basically a no-op on the Postgres side. You can rename something from food to bar, and we don't really need to change anything on Postgres. Because the ID hasn't changed.
All right. Thank you. Well, really appreciate it, Sully. We are in the home stretch here now. So to take us out and finally wrap up the inaugural EdgeDB day, I'm going to hand it back off to Yury to take us out with a bit about what our plans are for the future of EdgeDB. Yury.
Thank you, Colin. Oh my God, it went pretty smooth. Thank you so much for being with us today. Our journey to EdgeDB 1.0 took us many years, and words cannot describe how happy and proud we are today. And even though we now have 1.0 released, we're still at the very beginning of the path. As I mentioned before, we intend for EdgeDB to not just be open source, but to make the graph-relational model and EdgeQL itself an open standard. We naturally have big plans for EdgeDB too. It took us a relatively long time to build 1.0 because we were reinventing so many concepts from scratch. And we now have a rock-solid foundation with which we can iterate much, much faster. Expect to see a 2.0 announcement in just a few months. We're still figuring out the exact feature set, but the design process is already happening in the open.
Quick
Navigate
thing,
to
sorry to cut you
Yeah.
off, but I think you should. I think I'm spotlighted currently. So, I mean, I know
Yeah.
you want people to see my pretty face, but
That was my goal, actually, for sure. Right, I'm back to Spotlight. Anyways, what I was saying. So yeah, feel free to navigate to github.com/HDB and find the RFCs repo and check it out. Comment on the RFCs that are currently work in progress. We'd love to hear from you. So for 2.0 specifically, we plan to add a group by command to EdgeQL. And like the rest of the language, it's designed to be composable and powerful. We already have an RFC for it if you want to learn more. But we also want to implement a flexible access control layer and with which you will be able to specify access policies right into your schema and see them enforced automatically in your EdgeQL and GraphQL queries. We'll see if we have time to finalize the design and the implementation before 2.0, but we feel fairly optimistic about it. Next is a hosted version of EdgeDB. This is easily the most requested feature. We literally see people emailing and direct messaging us on a daily basis, asking us about cloud. And the answer is we are working on it. It's on top of our list. And just like with EdgeDB itself, building it around the developer experience will be the highest priority. From now on, you will be hearing from us pretty much on a regular basis. You'll see lots of blog posts and new live events. To stay up to date, please follow us on Twitter and join us on Discord. The links are in the video description. And by the way, give us a star on GitHub. That would mean a world to us. With all that said, I'd like to thank you all again for being with us today. We can't wait to see what you build with EdgeDB. And I hope to see you soon. Goodbye. Colin, is the plan to add the stream, to end the stream now?
I think so. Quick thing to mention though, if we are still streaming on YouTube,
Yeah, we are.
Yeah, EdgeDB is currently #1 on Hacker News. So if people want to go head on over there and join the discussion there, that's pretty exciting, and was not something that we necessarily expected. So yeah, the party goes on. It's just going to be continuing over in the HN comments. Yeah, I think that about plays us out. Really appreciate everyone coming.
All right. Goodbye, guys. Again, hope